So in this video, we come back to the question of how do we quantify the direction of a vector. This is one of those aspects of a vector, right? Vectors have direction and they have magnitude. So how do I specify the direction? If I tell you a direction, how do I do that? Well, I could do it in terms of, say, angles. So if I have the vector, let's say u here, well, I could look at the x-axis, I could look at the y-axis, and I could say pick the counterclockwise angle from the x-axis to u. That gives me some angle, let's say theta here. So what I could do is I could tell you all that and say this vector has an angle of theta above the positive x-axis as measured counterclockwise. So that's one way I could tell you the direction. Another much more useful way is to give you a unit vector in the same direction. So produce a unit vector in the direction of a given vector v. So how do we do this? Well, it's actually really easy with scalar multiplication and magnitudes. The way I can do this is if I find first the magnitude of v, that tells me the length, and then keeping in mind that when I scale a vector, if I look at the magnitude of the scaled vector, remember when we did this, CV, magnitude of CV is the absolute value of c times the magnitude of v. Remember that fact. If I scale the vector v by 1 over its magnitude, written like this, so this v, so this is the same as 1 over magnitude of v times v. That's another way to write what I've written here is v over magnitude of v. Keep in mind, I'm not dividing vectors here, even though I have a vector up on top and a vector up on the bottom here as a fraction. Keep in mind, I'm not dividing vectors by each other because magnitude of v, this guy here, this is a scalar. So it's okay to divide vectors by scalars. It's the same as multiplying by 1 over that scalar. So this is all itself a scalar. And it's equivalent to this. And now check it out. So if I do this, if I compute now the magnitude of this resultant vector, the scaled version of v over magnitude v. And yes, this is starting to get maybe a little bit complicated because I have two magnitudes going on here. So keep in mind I've found the magnitude of v, that's this quantity. I've now scaled my vector v by 1 over that magnitude, that quantity. And now, that's a new vector that I've scaled. And now I'm going to find the magnitude of that. Well, by this fact that we worked out earlier, this is going to be the magnitude of c. So that's the magnitude of 1 over, not magnitude, but rather absolute value of that, times the magnitude of v. But 1 over magnitude v will always be a positive quantity. So 1 over that's positive, so the absolute value is just itself. It's a positive quantity, so I can write it like this. I know that I don't have to flip any signs. Times the magnitude of v. And how beautiful is this? Magnitude of v divided by magnitude of v. Now I'm dealing with the algebra of real numbers. They cancel each other off. It just gives me 1. So that is v scaled by 1 over its magnitude. This is a unit vector. And what's brilliant is that all we've done is scale the v, and so it has the same direction as v. Notice that magnitude v that we're scaling by is positive, so it has exactly the same direction v. So it's a unit vector in the direction of v. So if I want to tell you the direction of a vector, it's enough to give you this unit vector that tells you the direction. Well, let's work out an example here. So find a unit vector in the direction of 2, 3. So 2, 1, 2, 3. And you can totally work this out with everything we've done. So if you want to pause the video and just work this out yourself, that would be great. Remember what the steps are here for actually working this out. We need to know what is the magnitude of the vector 2, 3. I need to figure that out. And then I'm going to scale 2, 3 by 1 over that magnitude. And that's going to give me a new vector. Again, the idea is, let me draw 1, 1, 1 here. This is -1. Here's my unit circle. The idea is I want to get a vector in the same direction as 2, 3, but whose tail is at the origin, whose head is on the unit circle. So a unit vector in the direction of 2, 3. This is what I'm after. So again, first off, I'm going to find the magnitude of 2, 3. Again, you really should try and pause the video and try and work out yourself. I'm going to keep going. So pause if you want. So that is, let's recall how to do that. Distance formula. I just want the distance between the tail and the head. This is in position vector form, and so I can write this as 2 squared plus 3 squared. That's 4 plus 9. That's square root of 13. That's the length of 2, 3 is square root of 13. Now I'm going to scale 2, 3 by 1 over square root of 13. So 1 over root 13 times 2, 3. And I'm going to write this in position vector form. This is 2 over square root of 13 and 3 over square root of 13. That's this vector. That's this vector right here that I was talking about. This guy is this. We've worked out exactly what it is numerically here. So that's pretty awesome. I'm just going to do a quick check just to kind of connect back to the algebra I just did. Let's find the length of this guy. Let's find the length of 2 over square root of 13. We're just going to check ourselves. It should have unit length. It should be length 1. Let's check. So this is going to be square root. It's position vector, so I'm going to square each of the components. Plus 3 over square root of 13. Square that. Oop, that's a pretty bad 2. Square that, so that's going to be 4 over 13. So this is square root of 4 over 13 plus 9 over 13. That's 13 over 13. That's 1. This is square root of 1. It has unit length. Brilliant. That's exactly what we wanted. We wanted this to have unit length, so we've checked that algebraically, numerically, and now we have it. That's great. So this vector represents the direction of 2, 3. So this is the direction of 2, 3. It's a unit vector in the direction of 2, 3. Now, what if I want a unit vector in the opposite direction of 2, 3? So let me draw this maybe in red. So here's unit vector in the direction of 2, 3. What if I want to go the opposite direction? Well, all I have to do is scale it by negative the length, which will just negate each of the components. So not too hard. So vector in the opposite direction of 2, 3, rather than being 2 over square root of 13, 3 over square root of 13, it'll be negative 2 over square root of 13 and negative 3 over square root of 13. And you can check it if you want. Find the length of this vector. You'll find that it's 1. And you'll also find that it's in the opposite direction. It is negative this, so the opposite direction of that. So pretty cool. This is how we quantify, or one, I mean, there's, as I mentioned, there's other ways to quantify direction. We'll use some of those as well. But this is theoretically, sort of algebraically, the easiest way, the best sort of way to quantify the direction of a vector is by giving a unit vector in the direction of it. And so this process here is one you're going to need to do a lot. You got to practice this. You got to practice taking a vector and producing a unit vector in the direction of it. This is, I kid you not, we're going to do this so many times. So many times. It's super useful. Okay, that's it for this video. I will see you next time.